In this video, we're going to be talking about stable isotopes in water and ice, and specifically how these stable isotopes relate to climate. We will discuss the major climate-related factors that influence fractionation between light and heavy isotopes. And we'll investigate what these mean about global climate and how we can understand it over hundreds of thousands of years. However, if you want to learn more about the basics of stable isotopes, what a stable isotope is and what the major stable isotopes of water are, please find the previous video linked in the description. To start out, let's look at carbon dioxide and hydrogen isotopes, or delta deuterium, from Antarctic ice cores over the last 800,000 years. Just as a note, the x-axis of this graph is given in kiloyears before present, thousands of years before present. So on the left, this represents 800,000 years ago, and on the right, that represents the present. Not exactly the present. We're probably looking at maybe 100, 150 years ago at this top value, because we don't see the modern anthropogenic warming here. Otherwise, we would see carbon dioxide levels reaching over 420 parts per million. But what we see in this graph is that there's a lot of variability in global climate over long timescales. There's this quasi-periodic variation, and also there's a really tight relationship between carbon dioxide and temperature. So what we're going to discuss now is why there's a relationship with temperature. Why do stable isotopes represent temperature? I will note that there are other factors that influence the isotopic values which arrive at an ice core and are recorded in the ice. But temperature is this overwhelmingly important factor. Let's talk about the factors that determine what water isotopes end up in glaciers. So one of the largest factors that influences isotopic values is mass-dependent fractionation. This works in two ways. So first of all, heavier isotopes will preferentially have stronger bonds. They're more likely to end up in water or ice, the solid or liquid forms, than to be vaporized. So this is because they have a lower vibrational energy, and therefore they form stronger bonds. Additionally, molecular weight itself affects some processes, such as evaporation. So if you think about deuterium, it's got an atomic weight of 2, which is twice that of normal hydrogen protium. Therefore, it literally takes more energy to evaporate it up, and that higher amount of energy is more likely to be the case. Just there is more energy around when it is warmer. There's more heat energy doing the evaporation. So deuterium will preferentially stay in the water, but that effect will be less strong at times when we have more heat. The same goes for oxygen 18 as opposed to oxygen 16. Next, we have Rayleigh distillation. This is a process you might recognize from the previous video on stable isotopes. So Rayleigh distillation is this exponential relationship that describes the partitioning of isotopes between different water masses. So as a water mass, like the water that's evaporated out of the ocean, moves farther away from the ocean, preferentially you will see the heavier isotopes raining out. Over time, this water mass in this evaporated water becomes more and more different from what is in the ocean. All this culminates in the water mass history having an effect on the isotopic value in the ice. So distance traveled impacts this. If the water mass has traveled farther from the location it evaporated at, then the isotopic values will be more depleted in the heavier isotopes. And if the water mass region of evaporation changes, this will be reflected in the isotopic values in the ice core as well. So some of the most depleted values we see are in very remote locations in eastern Antarctica. So as we discussed in the previous video, polar delta 18O and delta deuterium values are very highly depleted. The values are very negative. So this is actually going to affect the source reservoir as well if we're talking about very large amounts of water in the polar ice caps. For example, at the last glacial maximum, about 20,000 years ago, global sea level was about 120 meters lower on average than it is today in the late Holocene. This means that there was a ton more ice, largely stored in northern hemisphere ice sheets. In fact, the ice volume was enough, and this ice was depleted in the heavier isotopes enough that we can actually see the deep sea isotopic values changing. There are these calcitic microorganisms called foraminifera, and we look at the ones that are from the deep sea, the benthic forams, and we look at the isotopic values of this over time, and we see this reflection of global ice volume. It's also impacted by temperature, but largely what we're seeing is ice sheets growing and shrinking over time. So as glaciers grow, the ocean gets more enriched in the heavier isotopes. And as glaciers recede, the ocean gets less enriched. So we can see today the deep ocean is enriched to about 3.5 per mil, whereas at the last glacial maximum, this was about 5 per mil. And we can see all of this variation over long periods of time. Note that the y-axis here is flipped because we like to have the low values, which are during interglacial periods, correspond with higher temperatures. It's just to make different records match up better. It's an arbitrary convention. In the previous video, I mentioned that hydrogen isotopes tend to fractionate much more than oxygen isotopes. This is because of the mass-dependent relationship. So hydrogen isotopes, the heavier ones, are twice as heavy as the lighter ones. Whereas with oxygen, oxygen 18 is much closer to oxygen 16 in relative mass. So this mass difference, oxygen 18 to oxygen 16 is just an eighth of the mass of oxygen 16, whereas hydrogen deuterium is twice as heavy as hydrogen. So it's, the difference between it is that of a whole hydrogen isotope. Because of this, we see a slope in the relationship between these two species at around 8. This is called the global meteoric waterline. There is a y-intercept value of around 10. So here I have it theoretically, and here I have a paper or a figure from a paper from Lee Dansgaard back in the 60s showing one of the first, possibly the first, experimental data-driven depictions of this global meteoric waterline. There's been recent research showing the pretty complicated equations that govern how both source and site temperatures, that is, temperatures at the region of precipitation and temperatures at the region of evaporation, both impact the isotopic values that we see in hydrogen and oxygen records. These two records, hydrogen and oxygen, have very, very similar fractionation pathways. However, they are not identical. And so in ice cores where we have both hydrogen and oxygen records, we can differentiate the source and site temperatures over time. So here I have a graph showing source and site temperature anomalies from the Holocene over the last 800,000 years. And you can see that they change in about the same times, but not to the same magnitude, when the patterns are not exactly the same. So I just wanted to leave you with this stack of temperature records from a suite of different Antarctic ice cores to show you what exciting new research is being done and how stable isotope geochemistry in ice cores is being further developed today.